Welcome to this video on electricity generation and the national grid. We will cover how electricity is generated and how it reaches your home as part of your GCSE Physics revision. This video is divided into 4 main sections: how electricity is generated, the different types of power stations, the role of the national grid, and key exam tips. The big idea in electricity generation is simple. Almost every power station uses a turbine to drive a generator, which then converts rotational kinetic energy into electrical energy. While energy sources vary, they all aim to rotate a turbine. The 3 most common methods are using high-pressure steam, wind power, or moving water. A spinning turbine is mechanically connected to a generator. The generator uses electromagnetic induction, where coils rotate within a magnetic field to induce an electric current. Discovered by Michael Faraday, electromagnetic induction is crucial. A voltage is induced when a conductor moves through a magnetic field. Faster rotation and stronger magnetic fields increase this induced voltage. In fossil fuel power stations, coal, oil, or gas are burned to release thermal energy. This heat boils water, creating high-pressure steam that drives the turbine. The energy transfer chain in a fossil fuel station is vital for exams. Chemical energy in the fuel turns into heat, then kinetic energy of the steam, then electricity, with some losses as heat. Fossil fuels are reliable and produce large amounts of energy, but they are non-renewable and release greenhouse gases like carbon dioxide and other pollutants. Nuclear power stations operate differently. They do not burn fuel. Instead, they use nuclear fission, where heavy atomic nuclei, like uranium, are split to release vast amounts of thermal energy. While fossil fuel stations burn fuel and release gases, nuclear stations use fission reactions to heat water. Both ultimately rely on the steam-to-turbine-to-generator process. Nuclear power is reliable and carbon-free during operation, but it is expensive to build, produces radioactive waste, and carries the risk of accidents. Wind turbines are a renewable option. They convert the kinetic energy of moving air directly into electricity without any need for steam, boiling, or fuel combustion. For your exam, remember that wind turbines connect directly to the generator. They do not use steam. They are a clean, renewable energy source with no operational emissions. Wind power is renewable with low running costs, but it is intermittent, requires significant space, and can have visual or noise impacts on the local landscape. Hydroelectric power stations harness the gravitational potential energy of water stored at height. When released, this water flows rapidly through turbines, spinning them to drive the generators. Like wind power, hydroelectric energy is renewable and produces no carbon emissions during operation. It is also highly reliable because operators can control exactly when water is released. Hydroelectric power has advantages like being renewable, reliable, and carbon-free. However, it requires damming rivers, which can flood land, destroy habitats, and involves high initial construction costs. To help with your revision, this table compares the 4 main types of power stations. Note which ones use steam and which are considered renewable. Now let's look at the national grid. This is the vast network of cables, pylons, and substations that transfers electrical energy from power stations to your home. The process begins with electricity generated at 25,000 volts. It is then transmitted across the country at high voltages, up to 400,000 volts, before being reduced to 230 volts for your home. Why transmit at high voltage? It's a vital exam concept. Higher voltage means lower current for the same power, which significantly reduces energy lost as heat in the cables. Think of the equation P equals I squared times R. Because the cable's resistance is fixed, reducing the current is the only way to lower energy loss efficiently. Transformers are key to this efficiency. They use electromagnetic induction to step voltage up or down. But remember, transformers only work with alternating current, not direct current. Step-up transformers increase the voltage before transmission. They are found near power stations and have more turns on the secondary coil to boost the voltage for the journey. Step-down transformers do the opposite. Located near your home or businesses, they have fewer turns on the secondary coil, reducing voltage to safe, usable levels. In summary, step-ups increase voltage for efficient transmission, while step-downs decrease it for safe use. Remember that energy is conserved throughout these conversions. You should be familiar with the transformer equation. It links the primary and secondary voltages to the number of turns on each coil. You'll likely need this for calculations. Let's walk through a quick calculation. By substituting your known values for voltage and turns into the transformer equation, you can solve for the unknown quantity, like the secondary turns. That wraps up our overview of the electricity journey from generation to your socket. Understanding these steps and calculations is essential for success in your physics exams. You might wonder why we don't just use low voltage everywhere. If we did, we'd need extremely high current to carry the same power. which causes massive energy waste as heat in cables. Energy is lost as heat due to cable resistance. High voltage keeps the current low, making transmission efficient. This is why the national grid uses up to 400,000 volts. Memorize these three key values: 25,000 volts at generation, 400,000 volts for transmission, and 230 volts for home delivery. These are common in exam questions. In the UK, home electricity is 230 volts, 50 Hz alternating current. AC is vital because generators naturally produce it, and it is the only form transformers can work with. Here is a quick recap of essential definitions. Turbines convert kinetic energy. Generators use induction, and transformers step voltages up or down. Ensure you can define these clearly. Avoid these common mistakes. Always explain that high voltage reduces heat loss by lowering current. Remember, wind turbines don't use steam, and know your transformer ratios. Now for some practice. Pause the video and try answering these 3 exam-style questions regarding grid transmission, transformer calculations, and energy source differences. Here are the model answers. Ensure your explanations focus on the link between current and heat, and check your calculations for the transformer turns. Final tips: link voltage to current, remember Faraday for induction, identify which transformers go where, and distinguish between steam-based and non-steam power sources. You are ready. Keep these key equations and values in mind, and you will do great. Good luck with your exam preparation.